enriching session. It gives me immense pleasure to welcome Dr. Yashwant Kohli sir, who is the Assistant Professor in the Department of Mechanical Engineering at MNIT Jaipur, and he's also the co-coordinator of this very FDP. He did his graduation, post-graduation and doctorate from DTU and also pursued the postdoctoral research at IIT Delhi. Sir is someone I've had the privilege to learn from personally, and his sessions are always packed with clarity, curiosity, and deep technical insight. Today, as he will speak on materials and additive manufacturing fabricated by CMT, which is cold metal transfer, a subject that will beautifully combine the material behavior with precision manufacturing. Sir, thank you for being with us here today, not just today, but for guiding this entire program. We look forward for your session and the screen is all yours.
Yes, thank you for the nice introduction. So my slides are visible. Okay. So good morning, everyone. I'll be speaking about a fascinating and rapidly evolving field that is additive manufacturing using cold metal transfer welding process. So, or you can say it as CMT WAM. WAM means wire arc additive manufacturing. So we'll be discussing these things. So as we are saying, like additive manufacturing, often we are referring as 3D printing is a manufacturing process, especially for metals. So for our study, there are seven families of additive manufacturing, but for our study, it is basically dedicated to directed energy deposition. So it is further classified as a wire-based, arc-based system. That is the different processes, different power source we can use. For example, conventional GMAW, GTAW, CMT, and plasma. So my talk will be focusing on CMT. That is a low heat input variant of GMAW, which is you can say as an advanced version of GMAW. So CMT, that means a cold metal transfer welding process. So the terminology cold doesn't mean it's actually a cold or a cold power source or a cold melt pool it is making. It is a relative terminology as compared to conventional GMAW, as the parent technology is GMAW, gas metal arc welding. So CMT, the cold terminology refers to its uh, low heat input criteria. So this is the characteristics of CMT, which is having a very good uh, having very less spatter or negligible spatter consideration while joining also and while fabricating a single wall or a multi-wall components using additive manufacturing. Uh, so our talk is about wire arc additive manufacturing, which has already gained a popularity for producing large components, near net shape product, metallic components, uh, efficiently and cost effectively also. As compared to laser and powder bed fusion, this process is very economical and higher deposition rate you can achieve as compared to other laser and other processes. So this is the recent application I've gone through. It's a prototype subsea bonnet, which is fabricated by Robert Graham. He's a group welding innovation uh, scientist. So this you can see there are number of layers. So number of layers implanted one over the other. This is made from a CMT WAM process. Conventionally, if we have to make this component, this the subsea bonnet, it takes almost 3 months to arrive in a single roof and assemble it. But with CMT welding CMT WAM process, we can make this full component in hours or a 1 day under one roof also. So uh, that has been like a criteria that CMT WAM has that standard has been set. So while conventionally, if we are making this component in 3 months or arriving a single component and assembling this component in a single roof for 3 months, But CMT VAM has made it in a hours or one day we can manage. So this has reduced carbon footprints reduction, which is 60%. This is quantified with quantifiable carbon footprints. We can reduce it to 60% for this component. So you can assume, like, if we can fabricate any other components of navy or aircraft, aerospace engineering, that is taking too much time, we can fabricate in a single roof and we can reduce these carbon footprints, and it's a very good processes then. Okay, so typical applications with VAM are, you can see there is a wing spar titanium, made of titanium. These all are made with CMT VAM. This landing gears, this is also made by titanium. And you can see 10-meter aluminum alloy. This 10-meter aluminum alloy connecting rings. This is made for rockets. And this aircraft components, TI-6AL4 vanadium single wall structure titanium components are being fabricated. And this is very interesting. See, 6-meter long aluminum alloy spar by Cranfield University. This Cranfield University has a story behind that. Like, there is a PhD student, this student only. So there was a PhD student. He has passed the PhD degree and he has made a company called VAM 3D. So he's fabricating all the VAM components using CMT integrated with a CNC robot or CNC router or a KUKA robot or any other 6 degree of freedom robots. And he's fabricating many components, and he's a main company there in Cranfield University, and all are supporting this. So the components are very good, and that is made. He's made many components for rockets, landing gears, wing spars. So applications are widespread. So you can, um, if someone wants to work on this, they can easily work, and they can join the this group also. So this is wire arcade manufacturing. Basically, this is schematic VAM representation. Here you can see a wire feeder, and here this is the steel liner, and this is the wire buffer, and the wire comes out in the through the nozzle, and the weld bead has been laid. So you can see here wire feeder and the steel liner. Suppose if we are fabricating a hard components like hard material, suppose steel, inconel, nickel, titanium, so we have to use a steel liner. But if we are fabricating a softer material, for example, aluminum, magnesium, or any other softer components like copper, so then we have to use a Teflon liner. It is not like that you can use a steel liner with a soft material. That is theoretically wrong, and it will be a major problem while depositing a material. If suppose if you are using a softer material and you use a steel liner over that, so the somewhat problem will be that the arc stability will be a major problem, and the wire will be um, winding up, and it is uh, making a problem of wire uh, deposition. So this will be a major problem. So we have to stick with this hard. We have to stick with this theory. Like for hard materials, you have to use a steel liner, and for soft materials, you have to use a Teflon liners. So this is the wire buffer. This wire buffer in CMT, I will talk about the CMT process later. So this wire buffer is basically moving the wires, oscillating the wire to and fro in the CMT process. And you can see the nozzle here, and you can see here there's the substrate material, and this is the deposited material, gray color. And you can see this path strategy. Path strategy is an important terminology here, and this has a very impactful thing. Like if we are adopting a different path strategy, the mechanical properties may be different because of some anisotropy. So we have to stick with a good path strategy. In this In this schematic, I have adopted a bidirectional path strategy. You can see if we are depositing from this point to this point, and then the torch is moving a upward direction. Upward direction means that that is controlled by a stepper motors or servo motors. If you are having a CNC router, then majorly stepper motors will be contributing to the upward motion or the Z-axis motion. But if we are using a robot, KUKA robot or Yasakawa robot, then then servo motors will be responsible for high precision of moving upward. So if the torch is moved upward, then the deposition start from this point only, where it ended. So like this way, it has been deposited. It is called as a bidirectional strategy, and this will help in having a good mechanical strength, as we have deposited many components and we have tested it. So with my experience, I'm saying that bidirectional strategy will be a good thing, and we will get a good mechanical bond. So here, this you can see here a cross sectional view of the weld bead. You can see here the green color, the substrate material. This is the cross sectional view you are viewing from this side, and you can see the first bead, and the first bead, that is L1, L2, and L3. So there are three beads we have laid, three layers we have laid. L1, L2, and L3 are the deposited layers that we have deposited. But this L12 and L23, you can see in the diagram, L12 and L23 are the inner layers, which are automatically being made when the second layer is laid over the first layer. Then some dilution of a second layer in the first layer will happen. We can often refer this concept as a heat affected zone also. So it is basically a dilution thing or a heat affected zone. This is the weakest zone of the layers, and this L1 to L2 3 will be increasing as the number of layers are increasing in the building directions. So this L12 and L23, the inner layers concept is very important in VAM or single wall structure or multi wall structure, because if we are depositing, if we are having the width, this width of L12 more, that means the depth is more, then it should not be that much high and that much low also. It should be an optimum value. So if the L12 depth is more, then you will face a problem of height limitation. The height of the component will be less within the layers. So that means the average height of the length will be smaller, and that is not required in the VAM. So we need a bigger, if we are fabricating a bigger component, then we have to have a uh, good amount of height with less amount of layers. So if suppose if this L12 is very less, if you have kept it very less, so you will face another problem with a delamination. Suppose L2 and L1, the two layers will be delaminated if the L12 is very less. So it should be an optimum level. So that's why we are focusing on optimization of the weld bead geometry. So first we have to lay it over the beads, and we have to optimize the beads according to the dilution, reinforcement, penetration, weld width, and contact angle. So these five parameters has to be optimized. Then only we can start optimize, and the best parameters, process parameters will be the optimum parameter will be found out, and then that with optimized parameter we can fabricate a single wall structure or a multi wall structure. That will be a very good process. So during this optimization, this optimization part I will cover in the evening session, but that this the um, this is the standard procedure. Like we have to optimize the weld beats, and then after optimizing it, then only we can use the optimized process parameters. We can't directly take a hit and trial runs and like we can make a VAM component. Okay. So this is the classification of additive manufacturing. I've told earlier that is seven families of additive manufacturing, but I've indicated here four only, depending on the uh, material, wires, and powders, the type of materials. And for our study, it is directed energy deposition. This is the main classification of additive manufacturing in which we are studying. And this is further classified in powder based and wire based, and this wire based is further classified in energy sources, which is further classified in three types: laser, arc, and electron based. So laser wire is also a trending topic here, but it is very costly. Laser wire machine is almost around a crore. So the initial cost is very high, and the fabrication cost is also, it's not economical. So that's why we are preferring arc based, which is a best alternative, and we will get a almost similar strength and bulk material we can fabricate with the comparative densities also. So there's the third step. Third classification is electron based, which is also a very costly process, but the deposition rate is very high in electron based. So as compared to these three, we are sticking to arc based, and which is further divided into four criteria, that is GTAW, GMAW, CMT, and plasma. Sorry. So we can use any four of the power sources, and we can fabricate a WAM component. So with GTAW, everyone will be knowing about the power sources. This gas tungsten arc welding, gas metal arc welding, cold metal transfer, and plasma. So GTAW is having a typical deposition rate of 1 to 2 kg per hour. That is very less, because GTAW we have to feed the consumable, because tungsten is a non-consumable electrode. So we have to feed the filler wire with the hands, or we have to make a separate arrangement for GTAW for fabric for making a WAM component. So this is not if we are making a separate component, separate arrangement for that wire feeding, then it is a very good process, but the deposition rate is still very less as compared to GMAW. GMAW is having 2.5 to 4 kg per hour deposition rate, and CMT is having 1.3 to 3 kg per hour. Advantage is less or zero spatter with low heat input. So CMT is outstanding process welding process, which outstands these four. Like we can fabricate a component with a lesser heat input, because heat input plays a very important role in WAM component. As we are laying over beads, we have to control the heat input. Otherwise, the thermal gradient, if the thermal gradient between the top layer and the bottom layer is too high, then the problem of anisotropy will be very much in the material, and the properties will be differing in the bottom layers and the top layers. So that the transition you will see if you cut a tensile specimen or a hard micro hardness specimen, then the transition you will see in the materials if the this thermal gradients are too high. So if we can reduce the heat input in the power source itself, then we can attain a good homogeneous material, and we can get a good mechanical properties. So plasma is also like that, but we are considering CMT only. So this is the comparison of some representative AM processes. You can see with the wire additive materials and powder, this laser is having SLS is having zero point 0.1 deposition rate gram per minute, DLF 10, WAM you can see 12 gram per minute, and electron is having 330. So as compared to other processes, WAM is outstanding in its deposition rate, and it's in it shortened lead time. So the basic advantage of WAM is we can fabricate a 3D component. We can fabricate a multi-wall or single wall component by having a high deposition rate, shortened lead time, and it is very economical also. So as compared to other processes, these three advantages are having a higher demands. So we have to make a component with less time and higher deposition rate, and we can fabricate a near net shape product. That is almost we can fabricate a final component, and we can machine the outer surface, and we can sell the component. Okay. So here is the some increased deposition rate classification. This is the VAM product. You can see a large sample fabricated as VAM from Cranfield University. So this is the VAM component. This is the medium complexity and medium deposition rate we can achieve. So this is the basic cyclic loop of VAM process. We have to start the process, pre-shielding gases, we have to switch it on, and then arc we have to start, then first layer of deposition on the substrate material we have to do, and then final deposition. After final deposition, we have to post shielding gas should be on for 2-3 seconds so that the component will be cooled down. And then if the component is cooled down, we have to required interpass temperature. But this is very important. This interpass temperature concept is very important. As we are laying one bead, one layer over the other, we have to stick in mind, like the temperature in between the layers should be same throughout the building direction. Suppose in the first and second layer, the temperature you are making it 200 degrees Celsius. Like we have rested the component for 30 seconds, like dwell time we have given for 30 seconds, and the temperature has reached around 200 degrees Celsius. Then we can lay over the second layer, and then again we have to give a 30 seconds dwell time, and then that second layer surface, when it comes to around 200 degrees Celsius, then again the third layer has been deposited. Like that we have to do in every layers, so that we can attain a same interpass temperature throughout the material, throughout the building direction, for making a single wall structure or multi wall structure. As we are doing this, we are attaining a constant thermal gradient we can attain, and what we can achieve is a good homogeneous material 3D component we can make, and we can attain that. We can quantify that thing also with the tensile specimens, and 0 degree, 45 degree, and 90 degree we can take out, and we can test that material, and we can check whether the anisotropy is high or low. So that we have to check. Then again, if the interpass temperature we have made it, and then the start of second layer is being made, and whenever the component has reached its final height, we can stop the process. Or if it is not reached, we have to make another layer. Then again, we have to start the process. So it is a cyclic loop, and final we have to attain a height. For example, if we want to make a 100 component, we can final layer is being deposited, then we can stop the process. So this is the heat input concept. This is very important heat input concept. As I already told, thermal gradient should be constant throughout the building direction. So with this formula, eta vi by welding speed, so this we can use in the single wall structures. This formula, and this HIVAM, this is the volumetric heat input. That is this formula we can use for a multi-wall concept. Multi-wall, if we are making, then we can use this formula. Okay. So this is the basic difference between gas metal arc welding and CMT. So everyone will be knowing about the conventional process, GMAW. So I'm not going in deep with that, but for comparing, I will surely compare it. Suppose GMW is based, if we are comparing with CMT, is based on conventional short circuiting transfer. As we are learning in our BTech times, MTech times, like GMAW is having four modes of metal transfer, like spray transfer, globular transfer, pulse transfer, and short circuiting transfer. So for comparing with CMT, we are taking as a conventional short circuiting transfer mode for GMAW. And the droplet detachment, you can see the pinch effect in this GMAW thing, and this the melt pool. When the droplet detachment is responsible, the droplet is detached from the wire to the melt pool, the responsibility owns by a Lorentz forces. So Lorentz forces are none other than the electromagnetic forces and the gravitational forces. So these forces are responsible for detaching the droplet from the wire to the melt pool. So this is responsible for this droplet detachment, and the higher heat input concept is uh, having in GMW as compared to CMT. I will show the current and voltage waveforms here in the next slide. So CMT is basically it's a patented technology by Fronius of Austria in 2004. They have patented, and I have already told the cold doesn't mean it's a cold melt pool. It's a very low heat input transfer due to very low non-zero current. So at the time of droplet detaching towards the melt pool, the current intensity is very low. So we have reduced the current so much so that the droplet is detaching as a relatively colder droplet we have detaching, and we are delivering a lower heat input droplet towards the melt pool. So that's why we are controlling this heat input concept in this CMT. So here with GMW, Lorentz forces are responsible, but for CMT, only one thing is responsible, that is the wire oscillation movement. So that is controlled by digital process control. So here you can see with this is this is CMT machine that is available in Delhi Technological University. That in my PhD times I worked on this. So you can see in this oscillatory movement of a wire with a CCD camera. So this is very like it is very slow camera we have captured. Actually, in a single second, the wire is oscillated around 70 times. So 60 to 70 times the wire is oscillated. Then only that's why the spatterless and the low heat input concept is there in CMD. So this oscillation with precision they are controlling with DPC control, digital process control. So that's why it is a synergic welding process. So this is the main process, welding process, CMT welding process, how it is initiating. This is the arc initiation. Arc initiation comes with the wire coming towards the melt pool, and then the second phenomena is short circuiting phase. Short circuiting phase is when the wire just touches the melt pool. Whenever the wire just touches the melt pool, it is giving the signal to DPC, and DPC is retracting the wire with a wire buffer. As I told in the previous slide, the wire buffer has a uh, role of oscillating the wire. So DPC is the main brain behind the this welding process. So digital process control is controlling this wire with this much precision that it can make a 70 oscillation in a second. So after short circuiting phase, you can have a wire retraction. Just it touches, the wire is retracted, and lower heat input. This melt pool has been made, and then again the process is goes on and on. So this is the current phases. This PCP is the pulse peak current phase. This BCP is the background current phase, and this is the short circuiting phase. So in PCP phase, you can compare this in the current voltage waveform. This is the current voltage waveform. This red color line is the current waveforms, and the black color line is the voltage waveforms. And you can see in the initial thing, for a short duration of time, a higher current we have initiated, high pulse of current for a short duration we have initiated. And for this, the role is to make a droplet for the wire. At the tip of the wire, the droplet is made, and then again the current is lowered down in the background current phase. You can see the current has been lowered after the peak current phase. In the background current phase, the lower current form is taking place because to prevent a globular transfer. We don't want to increase the diameter of the droplet. We need a smaller droplet diameter. That's why the current has been dropped in the background current phase. Suppose if the current is not dropped and it is continuous at the higher current values, then the droplet droplet diameter will be more, and globular transfer will be taking place. That is the higher um, heat input we are depositing. So that we don't want in CMT. So that's why the current phase has been managed like this, so that the diameter is not that much and we can deposit a lower heat input droplet. So by this phenomena, we can reduce the spatter generation, and negligible spatter generation will be there in this phase. So after background current phase, you can see a short circuiting phase. This is the short circuiting phase. At this phase, you can see a voltage is dropped very low, around zero value. The voltage has been dropped. So zero arc voltage. Wire comes in contact with the weld pool. Wire retraction mechanism by digital process control. As I've already told, this is the head of the CMT machine. DPC controls all the movement of the wires, and then the droplet is detached and deposited. So this loop is controlling, and this is making a cyclic loop, and so that's why the droplet is detached. Sorry. So there's the main difference between GMW and CMT. You can see in a current waveform and a voltage waveform. You can see here, this is the current waveform of GMW. This is for CMT. At this point, the short circuiting phase, you can see increase in current values and increase in voltage values. So that's why the GMW can't resist higher heat input droplet. But with CMT, this is the advanced short circuiting transfer. We can control the current and voltage, so that at this very time, at the time of short circuiting only, we are controlling it. Otherwise, the second cycle and another peak current phase is happening. So at that very moment, we are reducing the current and voltage, so that we can control the heat input. So that is the phenomena behind CMT. So there's the pros and cons of GMW. Basically, it's with compared to CMT is having a major cons only. You can see higher thermal heat input, over penetration, cracks, high spatter, heavy distortion. You can see the A image. There's the stainless steel plates that has been welded, and this you can see a burn through over here. And you can compare the same with CMT. There is no burn through. So this is very good. And you can see in this image, there's the back surface of the bead, and you can see here the over penetration. This much penetration we don't need. This much penetration happens when the heat input is very high. So with the same current, you can see CMT is having a very good bead, and at the back nothing is over penetrated. And with the GMW, you can see some cracks also in at higher current values. And you can see here at the D image, heavy distortion. You can see this much distortion we don't need in WAM. Otherwise, the layers will be also will be distorted, and the component will be ruined out. So this we don't need. So that's why we are preferring a colder or a lower heat input concept in WAM in additive manufacturing. So CMT offers spatter-free weld, very low thermal heat input, high gap bridging ability, and negligible distortion. So this is the CMT. This is the uh, development I've done in IIT Delhi. Development of CNC integrated WAM setup. We can use multiple torches in this. I have integrated GMAW torch. We can integrate GTAW torch also and CMT also. And you can see here. So this development, I was using open build software. So we just have to give any shape if we want to give any shape, and you can the shape you have to give the tool paths, And after toolpath, you have to configure the toolpath, and then the software itself will generate the G, and the software will automatically generate the G codes, and the G codes can be used for fabricating a 3D component. Here you can see the images. Here you can see the images of single wall structure here, and I've made this hexagon shape also. This this is not playing. So at the end of the video, you can see like how the toolpath is configuring itself and making layers over the layers. So this hexagon, uh, this auxetic structures I tried, and this is very good as the finishing, and this precision is very good, like point less than 0.05 or less than 0.5 mm of precision is there. You can see at the end what I'm trying to say. So now you can see there is a very hot layer at the top layer. Top layer will be very hot. So we have to give a dwell time over here for 30 seconds. Then we have to make it as a we have to wait for cooling. And then the third or fourth layer, the n number of layers we can implant. So the temperature gradient should be evaluated or quantified. Then only we can make a good bottom to top structure. So the same setup I have made with the GTAW setup also. So conventionally GTAW, everyone have seen, we have to feed the wire in manually. So what I did now, we have used the same torch for GTAW, but this side arrangement. So I have made a wire arrangement here, and I have used this cold wire feeder here, and this cold wire feeder is automatically feeding the wire, and this it is coming out from this wire movement, and it is at an angle of 45-degree. So we can control this wire movement, this arc movement uh, at at its synergic, like both are making at the same time. So that's why it is having a very good, we can fabricate a very good WAM structure here with this setup. But the problem is that, as I've told you, GTW deposition rate is very less. So that's why it is taking too much time as compared to GMW or CMT. But the accuracy or the surface roughness on the sides will be the surface finish of the component will be good in GTAW fabricated component as compared to GMAW or CMT. So this is the basic beads we have tried. Like as I've told you, first of all, before making the WAM component, we have to try a single bead for different process parameters at which at what is the best possible process parameters, optimized process parameters for which we can go for WAM component. So these are the multiple range we have taken, 20 to 24, and wire feed rate and welding speed. So multiple beads we have made it, and among these beads, which bead is very good as compare as per the bead aesthetics. The bead aesthetics is very important concept for making a WAM component, as the process parameters is playing a very important role in controlling the reinforcement height, the penetration, the contact angle, the dilution percentage. That should be an optimum thing. That then only we can check the same process parameter with the WAM component. So for thermal gradient, for temperature profile, what we can do is uh, we can use thermocouple, K-type thermocouple for thermal monitoring, and the thermal imaging camera we can use. Both I have used, and the difference is not that much, like plus minus 5 degree we can achieve in both the things. But we have to use a thermocouple or a infrared thermal imaging camera so that we can control the interpass temperature. Interpass temperature has to be same in between the every layer as we are building in the uh, Z direction. So this is the case one that I have. This is the published paper that that I can talk about. This is the aluminum material that we have made it, and you can see there is two path strategy: unidirectional and bidirectional. So this WAM component I have made with two path strategy: unidirectional. That means we are depositing from one direction, and the same point we have to deposit the second layer at the very same point. But in bidirectional, I have already told, we have deposited from one point to other. The end position we can start the deposition on the second layer. We can start the deposition on the that very point. So with this, we have concluded this thing, that bidirectional strategy will be very good. As you can see, this sample fabricated with unidirectional will be having these types of problems. You can see a cavity formed in this while making a sample with unidirectional, and this is considered as a material wastage. We don't want to waste a material, as if we are comparing with the conventional material. In conventional fabrication process, the material wastage is very high. So why we are adopting additive manufacturing is we don't want to waste the materials. So so this path strategy is not working. So that's why we did with the bidirectional strategy. You can see how much difference is there, which is the same parameter. This is 50 ampere current. This is also 50 ampere current. Just the path strategy difference can make this much lot of difference. You can see the shape of the single wall structure here, and you can see the shape of this. And and if we are increasing the current or the heat input values, so we can see the humps over here. This is also a defect in WAM. This is like a camel hump. If you can see, you everyone have seen the camels. The camel hump is like this camel hump is like this. You can see here many humps are formed. This is also a defect which is deteriorating the mechanical properties. So I've written the paper like this, only controlling of humping phenomena. So for WAM component, we have to reduce this humping phenomena so that we can achieve a better mechanical properties and other microstructure properties. So the same component has been made with tensile specimen at 0 degree, 45 degree, and 90 degree. So what we have observed is, uh, all the tensile specimen has been tested, and you can see the red thing is the 50 ampere bidirectional at 0 degree. So 0 degree orientation is having a highest strength as compared to this 90 degree, because in this the layer is in the transverse direction. So that's why this is the weakest tensile specimen. This, and 0 degree is the strongest tensile specimen. But the difference is not that much. So we can conclude this. We can conclude the statement like anisotropy is very less in this. That because we have made a dwell time, we have made a constant dwell time of 30 seconds to 1 minute. So if we are controlling the temperatures, we can fabricate a good component, a bulk component. We can compare the density with Archimedes principle, and we can compare the density for a conventional material and a WAM fabricated material. The density is very I have tested this density, and it is very close to the conventional material. So that we can say it's a bulk component, and the porosity levels are very less. So that uh, is very good, as we can fabricate a 3D component, a complex shape of component we can fabricate, and a bulk component we can make it with the additive manufacturing. So for conclusion, for this slide, for this paper, is bidirectional strategy is an effective method for layer manufacturing due to lesser material wastage and higher product reliability. Humping defect plays a vital role in reducing the tensile strength and percentage elongation. And humping defect can be controlled by selecting the low heat input process parameters. So this is very important. By considering lower heat input parameters only, we can mitigate this humping defect. Otherwise, humps will be formed in softer materials. It is very susceptible, but in harder materials, we can eliminate this. So this is the next paper, material characterization journal we have targeted and we have published it, influence of heat input on evolution of delta ferrite. This is a stainless steel material we have fabricated. So you can see multiple layers in the building direction. We have extracted a square shape 10 by 10 specimen we have extracted, and we have tested that this is an austenitic stainless steel, that is SS308L. L refers to a low carbon content, that is 0.03%, less than 0.03%. And uh, in the raw material, the wire is austenitic, but when we are melting and laying it in the layer form of layers, heating and melting, so the solidification criteria is like that. We are assuming we have observed that it is following a FA mode of solidification, that is ferrite and austenite mode of solidification. That means ferrite is forming some portion of some percentage of ferrite is forming in the austenitic phase, and majorly it is austenitic, but some percent of ferrite is there. Sorry, that you can observe in the microstructure also. This the gray portion is the austenitic phase, and this the grain boundaries are settled as delta ferrite. So delta ferrite, gamma austenite, and micro inclusions are in the microstructures. This thing we can quantify these values also with the microstructure images. Also, we can quantify, or we can have a ferritoscope. Also, we can calculate, we can quantify this ferrite percentage, how much ferrite is there in the material. So this is this image refers to the ferritoscope image. So ferritoscope is basic principle is magnetic induction principle it is based on. So as we know, delta ferrite is magnetic in nature, and we know austenite is non-magnetic. So with this stylus, we can touch the specimen, and this stylus will check the magnetic properties. And if some ferrite is there, then it will show in the display like how much ferrite percentage will be there in that sample at a specific point. So at with that stylus can be rubbed over the surface, or we can take a different points, we can mark it, and we can measure the ferrite percentage also. So you can see I made three components with different process parameters. It's a minimum heat input 234 joules per mm. One component is made of this heat input, and this is the highest heat input 643.2 joules per mm. So with higher heat input component, WAM component, we are getting almost 13% of ferrite content, and with the minimum heat input we can see 8% of ferrite. So as per the literature also, 8 to 12 percentage ferrite will be there if we are fabricating a SS308L or 316L or 304L. So these ferrite is very important, as I will tell you in the next slide. This will prevent the transgranular corrosion also. So in the sensitization thing, I will tell you. So here in this graph, you can see as we are increasing the heat input, the average grain size is increasing. As we know, the Hall patch relationship is as we are increasing the um, grain size is increasing, the micro hardnesses reduction will be there. So the red line will be micro hardness reduction. So this is confirming that Hall patch relationship exists in this component. And this is the multiple layers you can see. This is the inner layers. This eye-shaped structure is inner layers. This is the interlayer. So this is the structures we are observed with the after polishing and in the microscope, optical microscope. So with this paper, what we have observed that delta ferrite has its own six morphologies, that is lithiferrite, vermicular ferrite, columnar ferrite, serrated ferrite, globular ferrite, and acicular ferrite. So these are the six delta ferrite morphologies we have measured, and we have quantified it also at different locations. How with the different heat input, how it is quantifiable. Like with lower heat input, 30% of the lithiferrite will be there. As we're increasing the heat input from top to bottom, you can see the gray portion will be less. So lithiferrite is reducing, while the red portion, which is vermicular ferrite, is increasing in the increasing heat input. So these are the two major morphology of delta ferrite, that is lithi and vermicular ferrite. So that you can see in the optical microscope images in the in the transition zone, like in when the layer is changing, there is a major portion of globular ferrites, while in the interlayers we are experiencing a vermicular ferrite and a lithi ferrites, while EDS and these graphs are there. So major conclusion is, as the heat input increases, the gamma austenite concentration decreases and delta ferrite and micro inclusion increases. With increasing heat input, Lethi ferrite transforms into faceted morphology, while vermicular into globular ferrite morphology. So this is the major conclusion, and we have made a good results out of that. So this is the next paper, wear characteristics of wire arc additive manufacturing. We've used a pin on disk rotation, pin on disk machine for, we have extracted three pins out of that. We have multiple components. We have 27 pins. I have made it, and then we have checked. You can see this graph is very important, and we are think this blue color line is prior to wear test. We have checked the XRD plot. This blue color, we don't have any martensite here, only delta ferrite and gamma austenite is there. But after the wear test, what we are seeing, wear debris is red in color and black in color is worn out surface. So worn out surface is experiencing a martensite structure. So as we are going with the wear test, the stainless steel will be plastically deformed, and it is changing a phase. Phase transformation will be taking place from some martensite will be forming, that is magnetic in nature. We can check with the ferritoscope how much martensite or how much ferrite will be there. So that we can quantify also. And this is the wear characteristics. So wear is also coming very less, as we are having a very high load, 120 Newton, 150 and 180 Newton. Still the wear rate is very less. So that this additive manufacturing component is very good wear resistant material. And you can see micro hardness from the bottom layer to top layer, it is decreasing. So why it is decreasing? Because of its thermal accumulation. So from bottom to top, there is thermal gradient is difference is there, and the thermal accumulation, the heat accumulation will be there in the layers. So that's why the due to heat accumulation, the grains will be wider or grains will be larger in shape in the top region. As the grain size is more, the hardness will be reducing due to Hall patch relationship. So that we can understand. So this is basically the wear rate we have calculated, and the plastic deformation we can see. Higher heat input induces low hardness, which in turn causes more plastic deformation than lower heat input. As the load increases, plastic deformation transforms austenite to martensite, reducing ferrite concentration. So these are the major outputs of this paper. And this is the work that my MTech student has done in IIT Delhi. So this you can also do the work in joining of VAM component by diffusion bonding. This is our this in this concept we are the pioneer for this topic. As in the Science Direct or any other journals, we don't find these papers. Only 3 to 4 papers are there, which we have only published. So this is the new emerging topic. With diffusion bonding, we can join the VAM components for the application of heat exchanges. So for heat exchanges, we can develop this technology, and we can make a good bond out of that. So we have done it like the same machine my MTech student has used, and he has fabricated a single wall structure of aluminum and stainless steel. And prior to that, this is the optimized process parameters only, as I have already discussed. Like it has been optimized, the well bead has been optimized, then only the optimized parameter has been used for the component, the 3D component, and then mechanical properties has been tested for VAM. You can see a diagonal specimen is having 629 megapascal, whereas the conventional material is having 550 megapascal. So we have achieved a higher tensile strength as per the conventional material also. So that is a significant change what we have done it. And there's the high hardness and this thing. And he has made a diffusion bonding of dissimilar materials and similar materials also. You can see here VAM stainless steel SS308L, and this is the uh, aluminum side, this thing. And you can see this white portion, white line, whitish layer observed at diffusion zone. This is possibly the intermetallic compounds has been deposited in the bond line. So bond line is free of porosities and void and cracks. So that's why the shear strength shear test we have done it, and the results are very promising. And he has failed also, like he has done steel and aluminum, and this has been like aluminum has been deformed in the diffusion bonding machine. But with prior, like with the continuous efforts, he has made with the rolled sheet, aluminum rolled sheet, and VAM fabricated this stainless steel. So the bond line is very strong, and we have made a component out of that. So that component is very good, and the strength is very good. So this is the new concept that we can make a VAM component, and we can bond with the diffusion bonding concept for a heat exchanger applications. So everyone working for in this field, we can use this technique also. So everyone knows that EDS thing is this for elemental analysis, but for with my experience, EDS is not that much accurate. So people should do EPM analysis, that is electron probe microanalyzer, which is like which is giving a accurate quantified results, like how much percentage of iron, aluminum, chromium, nickel, or silicon will be present at a particular point. So at we have done it in 4 point, like when two in the bond line and two in the base materials. So this is giving the exact percentage, and EDS doesn't give the exact results for atomic number less than 10. So for atomic number less than 10, we have to consider EPM analysis, because for EPMA, the accurate results will be there for less than 10 atomic numbers. For suppose we have to quantify nitrogen percentage, so we don't want don't inaccurate results. So EDS we can skip it, EPMA we can do it, and it will measure the exact percentage of nitrogen, oxygen, all the things. So I think time is up, but I have to discuss more of these things. Later on, we can discuss in the evening also. I have two lab sessions. I will complete this, and then we can um, switch to the design expert software, and we can make that. So the last thing I can share this sensitization, like as I've already told, 3SS austenitic stainless steel 308L. Why we are using it? Because it has a reduced carbon content, that is 0.03 percentage, while conventional it without L, this thing, it is having 0.08 weight percentage of carbon. So this is very good thing if we want to um, lower down the sensitization problem. Sensitization is like the chromium carbide formation will be there in the grain boundaries. You can see this is the grain boundary, and chromium carbide formation is highest in this. But adjacent to the grain boundaries, you can see the chromium depletion zone. These zones are very weakest zone against the corrosion thing. So in this point, the cracks will be formed. You can see here at the adjacent to the grain boundaries, the cracks will be formed, and the corrosion, the transgranular corrosion will be affecting the material. That is deteriorating the material. So this is not good. The why, how we can mitigate this problem by using the L number like 304L, 308L, 316L, L type of material. And we can use a solute also, niobium, titanium, vanadium, tantalum. These are having a higher affinity as compared to chromium. So it won't be a chromium carbide formation. It suppose if we are using a niobium solute, so niobium carbide will be forming. So this is very good, and this won't be having the corrosion problem. So in this, so in the market, stabilized stainless steel materials are also existing. 321 you can use, which is a titanium stabilized material, and 347, which is a niobium stabilized material. So these can reduce the sensitization problems, the corrosion related thing. And if you are aiming for a submarine applications or navy applications, these stainless steels are very much used, and you can use these type of materials which are corrosion resistant. And these are the Schaeffler diagrams. And yeah, at this time, I will end it. Like, any questions, I'll answer. So thank you for your attention. I'll now take any questions if there are.
People having questions, please write in the chat box.